So we've talked a little bit about how the magnetic force interacts with moving charges. But what happens when you have a collection of moving charges, right? When you have a current. So here what we have is a current carrying wire, which, as we know, is a collection of charges that are sort of moving from left to right in this case. And we're going to stick that current carrying wire in an external magnetic field. So the magnetic field that I'm going to draw is not the magnetic field that's due to the current in this wire, but it's rather a magnetic field that is a result of other wires and charges somewhere else. So in this case, what I'm going to do is I'm going to say that I have generated a magnetic field that points everywhere into the board due to currents and charges that exist in other places, okay? And so the idea is to try to understand, well, what then happens to this current carrying wire when it is placed in this magnetic field? So the way that we're going to model that is we're going to take a little slice of the wire and try to understand what happens to that, and then we're going to add up all the parts. So we can do that because our initial model that we have is that on a single charge, the magnetic force that's applied is equal to QV cross B, right? We've worked with that a little bit. So that means that if we have a little piece of charge, right, a little piece of moving charge, then the differential amount of force, that is the little bit of force due to a little bit of charge dq, is going to be dqv cross B. This is exactly what we did when we derived Biot-Savart's law, right? We had this sort of dqv situation. What we did was we took a little chunk of the wire and we referred to it as having a dl, a length dl. And we also posited this idea of having a vector dl, which points in the same direction as the current, if you remember. And so what we did was we said, well, this dqv is exactly equal to dq dl dt. We transferred the dt over to the dq, and we got that dqv can be written as the current times dl. So in fact, that little differential element of force, that is the amount of force that is applied to a little chunk of wire, is going to be equal to the current times dl times B. So how do we find the force that acts on the whole wire? Well, the force that acts on the whole wire is the sum of all of the little bits of force. Let's pause for a moment, though, and look at what the direction of that force is going to be on that little chunk of wire. So if dl points in the same direction as the current, we point our fingers in the direction of the current, or in the direction of dl. We curl in to the direction of B, and our thumb points in the direction of the force. So this little differential element, this little piece here, is going to experience a push up. So there will be a little bit of df that is applied to that little piece of wire that points up. Now if you look at every little piece of wire along the way, and we think about this magnetic field as being uniform, you'll notice that every little piece of wire is going to contribute a df that points upward. And it'll all be roughly the same size and so forth. And so the overall force on this wire is going to be upward. Let's see how that'll be the case, right? So what we're arguing is that the total force that acts on that wire is the integral of all the little chunks. And so what we have to do is add up all the little chunks. So starting at some initial location and going to some final location, we integrate IDL cross B. Now what we'll do is we'll make some assumptions to make this a little easier on ourselves. We've only dealt with steady currents, that is currents that have a uniform flow and therefore are constant over the whole domain that we're interested in. So this current can actually be pulled out of the integral. And so what we're going to have is the integral from some initial location to some final location of dl cross B. Now we can worry about the magnitude of this situation, knowing that we can get the direction from the cross product. And so what we can do is reduce this problem just a little bit by saying we care about the magnitude. And so what we'll have is this integral of Li LF of dl B sine theta, where theta is the angle between the magnetic field and the dl vector. Now, in our case, we're going to only work with these magnetic fields that have uniform characteristics. That is, that they have a constant value and a constant direction. And so this idea that the magnetic field here can then be pulled out of the entire equation is also related to the fact that their direction will not change relative to L. That is, we're going to deal with wires that don't have some funky shape to them. We're going to deal with wires that are straight and have magnetic fields that are around them that are constant. And so as a result, what we'll have is we'll be able to take both the magnetic field out and the orientation between the magnetic field and dl out. That is, sine theta will be sort of this constant value. And as a result, we're integrating just dl. So what that gives us is then just the length of the really long wire that we're interested in. And so the total magnetic field, magnetic force that's exerted on that wire is just going to be the current times the magnetic field, which is a constant magnitude, times the length of the wire, times the sine of the angle between the wire and the magnetic field. Okay? So in this case, the wire is perpendicular to the magnetic field, right? So the sine of that angle is 1. And so in this case, if we added up the whole length of the wire, we would just have the current times the magnetic field times the total length of the wire. But you could have magnetic fields that are oriented in different ways, and so you'll have to determine what the angle associated with that is. Now, once we have this magnitude, you might say, well, how do we determine the direction? Well, we go back to our discussion that we had earlier. How does each little piece of the wire contribute? So we look at the cross product. We look at I dl cross B to get the direction, and then we add up all the directions. Do they all point the same way? Do they collude in some way to give us something that looks different? And so forth. So what we did in this video was we started from the model for the force on a single charge. We sort of abstracted that to a chunk of moving charge, and then we made some assumptions to figure out what the total force would be on a piece of wire that's long and straight and in a uniform magnetic field with a steady current.